Welcome back from lunch. Everybody is now time to put your heads down and take a nap. No. All right, people are getting their last coffees. So, but I'll say,
wait till Barry comes in. That will be the signal
that people have actually been shepherded. That's the word I'm looking for. There was a word that I can't remember. Anyway, it's Wednesday afternoon. Why did I sign up for the last slot?
Sign up.
Sign up. Well,
I got volunteers before.
I said I wanted the last word.
And you got it.
Yeah.
For better or for worse.
That's right. All right, cool. So, welcome back. This is it. This is it. We're almost done. We can all make it appropriately caffeinated. We'll manage. So, technically, this is supposed to be the what have we missed session. And since everybody probably has just had a little bit of time to think about that since we finished the morning, if anybody does want to send me a slide, or actually probably easier, just put it in the Dropbox for this afternoon, and we can talk about that. I also have a couple of other things. So, as Jillian said, I did have a slide for the observables, and some of you have probably seen this before. This is basically, this is taking things that LIGO has already observed and using them to set some constraints on AGM. So I don't know what the right fraction of events is for LIGO, but I think I know how many events I might get in a certain type of universe. And in particular, right, there's lots of different kinds of AGN, but if you count every low luminosity AGN in the universe, they're 30% of all the galaxies. And so that's a lot. And in order for all of those low luminosity AGN to matter to us, then there must be some amount of gas in them, some gas disk. And that gas disk, since they're low luminosity, must be a radiatively inefficient accretion flow. And that's very handy, yes.
Why?
Oh, sorry, yeah.
Why does it have to be radiatively inefficient as opposed to simply being a low accretion rate?
Oh, right. So that's actually better, right? So there are two options. Sorry, yes, I should be clear. So either they are low luminosity because they are radiatively inefficient, or they are low luminosity because there is just not a heck of a lot of gas there. So in the case where there is not a heck of a lot of gas there, then we don't really care so much because they're not going to impact the dynamics of the nuclear star cluster to such an extent, because there's, well, for low enough gas.
How much gas is not enough is perhaps an open question.
Yeah, so answer this one, right?
What's that?
So it's an open question.
Yeah.
It's an open question, but we're talking about like things that are 1,000th the mass of the central object. You know, in order to match our observations, they're very low mass, and they're going to have to be very.
For 10 to the minus, say 5 or 6, Q of 10 to the minus 5 or 6 for the orbiters, 10 to the minus 3 disks are still going to be pretty massive. And I think you'll get some migration effects down to disk masses that are, a few times, what would you say, Vlad, 10 times the mass of the orbiter?
Integrated disk.
Integrated disk mass compared to orbiter mass. How much do you need to push the orbiter around? 10 times the orbiter mass?
Well, let me skip over this by saying, if they are they're either radiatively inefficient or they are radiatively efficient. If they are radiatively efficient, then they are thin because they are, and there's not a lot of mass in them, relative to Seyfert galaxies, and they are therefore not filling very much of the volume of the nuclear star cluster.
Okay.
Can we go with that?
We can go with that.
Okay. So we're not filling very much of the volume of the nuclear star cluster, which is actually the important point. So if you say that a third of all galaxies have, so 30% AGN fraction, or 30% AGN fraction, and you say that a typical nuclear star cluster has a few by 10 to the 4 stellar mass black holes in it, which I think is reasonably well motivated from our own galactic nucleus and theoretical calculations, then you can compute what the rate of mergers would be based on this, and I believe that Barry talked about this on the first day, this sort of naive Drake equation for the rates. The rates depend on the AGN fraction, the stellar mass black hole number, the binary fraction, and the fraction of objects that end up in the disk. So this is why the volume filling factor of the disk or the radiatively inefficient accretion flow matters. So even if you don't think that there's any grind down and you only account for things that are going to be in the disk anyway, if you have a radiatively inefficient accretion flow, it is geometrically thick, always. And so we can say that just what fraction of objects will be in the disk, or will be embedded in the flow, we can just do a very simple, naive, geometric assumption and say that for a constant aspect ratio flow, take that cylinder and divide by the spherical volume, and then that's going to be the fraction in the disk, at least to start with, because that's the volume that you're taking up. So you can relate the fraction in the disk, fraction of stellar mass objects in the disk, to the aspect ratio h/r of the flow. Radiatively inefficient accretion flows are all, this is in log, so they're all way up here near the top of the axis. If you assume, you do have to assume some kind of binary fraction, and here I've assumed a binary fraction of 1/10, which is, I think, not a lot of special pleading. It's not a really obscenely high number. It might be even higher than that. But the other thing that it depends on, the last thing that it depends on, is the lifetime of the AGN disk. The reason it depends on the lifetime of the AGN disk is as long as the binary lifetime is less than the lifetime of the AGN disk, what's dominating how many mergers you get is how long the AGN lives for. Once you've used up everything in the disk, then you're done, right? You can't have any more mergers. And this, we think, is generally true. So what I've got here is what is the rate that you get just given these parameters. 30% AGN, fraction, 10% binary fraction, pretty rational number of black holes in the nucleus, and then here's your h/r, but really I've calculated using the fraction in the disk, and so this is just geometry, right? So these are the really fat reafs up here, and you can look as a function of the AGN lifetime. This is in log of megayears, so this is 1 megayear lifetime, and this is 100 megayear lifetime. And what these gray lines are, they're sectioning off the LIGO rate right now. So these are the LIGO limits right now. So right now, I can tell you that if you believe that all liners are reafs, then liners have to live for an exceptionally long time in order to keep us under the LIGO upper limit. So there, I just did some astrophysics, some AGN astrophysics with only the LIGO rate.
I'm trying to understand the plot. What is FP again?
Oh, sorry, the microphone. Yeah.
Oh, sorry, yes.
Yeah.
Yeah, I'm trying to understand the plot. What is again FB and FD?
FB is the binary fraction, and FD is the fraction of stellar mass black holes that end up in the disk. But with a radiatively...
Of the whole galaxy?
No, just of the nuclear star cluster. Right, so we have 10 to the 4 stellar mass black holes in the nuclear star cluster. You have this huge, fat, radiatively inefficient accretion flow. It's taking up almost the whole volume, and so you get a large fraction of those objects embedded in gas.
And that's why it depends on the day scale height.
Yes, exactly. Yeah. So that's the aspect ratio. So if you have a big fat volume filling gas and you have this typical number of stellar mass black holes, even for a pretty low assumed initial binary fraction, if that's going on in 30% of all galaxies, you will get a stupid number of mergers. So, yeah.
Another type of calculation.
Oh, is that on?
Is it on?
Yeah,
Yeah.
now it is.
So yeah, so another type of calculation that one can do is just ask what would be the merger rate if you, independent of AGN, if you just merge all of the black holes in the galactic nuclei once per Hubble time. So let's assume you merge all of the black holes within a Hubble time in all of the galactic nuclei. It turns out in that case you get a number something like 30 per gigaparsec cube per year, which is lower than your upper limit. And I think the reason is that here basically you're assuming that you're merging your black holes within the amount of time shown on the x-axis, right?
Yes.
And then you're regenerating a population of binaries over those timescales again and again and again.
Yes. So that is right. So this is weird because this isn't what you naively expect, because the longer you have an AGN on, it's the lower rates are for longer lifetimes, which is weird. But the reason why is because, yes, we are assuming that if you have an AGN that lasts for a megayear, then you're going to have a period of quiescence that's longer than that. And that gives you the opportunity to repopulate, right? We know that the rate is higher, or we don't know that. Well, yeah, no, what's the lower limit? The lower limit is, I put it in the plot, but now I've forgotten what it is. It's like 10, right? So, like, okay, so we don't know that the lower limit is higher than 30, but it's well within the range of plausible that that LIGO is seeing more than 30 per cubic gigaparsec per year. So by your argument, right, then that should not be possible. But so what must be happening is you make new black holes. And so this is the point that I've been trying to say actually a few times. You make new binaries, and you make new, and you make new black holes, right? So you have a period of quiescence, and then you, during that period of quiescence, which is always longer than the period of activity, you have time in that quiescent period to make new black holes and to make new binaries. And in fact, the reason why it goes as the inverse of the lifetime is because what happens is the gas processes, right, are the things that we have been looking at imply that the gas processes go quickly. Amy's work says that binaries form pretty quickly in the disk, well under a megayear. And so, maybe they don't actually harden to merger in that time, and we can, that's definitely on future work. So yes, we are assuming that they come together and they harden. But if everything happens in the first megayear, what matters is how many episodes of AGN activity you get per galaxy within the LIGO horizon. And most of the time, people have been assuming you get one episode, but that's not necessarily right. You're actually implicitly assuming something about the AGN fraction and the AGN lifetime by doing that, and that may not be right at all. So if you get, basically each time, if you have a period of quiescence, the nucleus relaxes, you get a bunch of black holes that are now doing whatever they're going to do. You have new black holes delivered in by dynamical friction. You've had some episodes of star formation. You have some binary formation, and they're pretty dynamically hot. You drop the gas disk on it, and then they dynamically cool, they find each other, they make binaries, they have mergers, and then you get, but then that process slows down. So the longer the AGN disk lives, the less mergers you get per unit time, but you don't know which AGN just turned on and which didn't. You just know, oh, that's an AGN, that's not an AGN. So looking at it, we just have to average over the whole thing.
Couldn't you also say that this is a way of measuring the duty cycle?
Oh, sorry.
So this comes back to one of our email conversations.
Yeah.
But wouldn't this be a way of measuring the AGN duty cycle by seeing this increased rate of mergers?
Yes, I think, no, that's exactly my argument, right? My argument is I just measured the lifetime or the duty cycle, however you want to put it, right?
Yeah.
Like, basically, we just did, right? There you go. The AGN lifetime for low luminosity AGN, if you want to say that they are fat volume filling reacts, then you have to say that they are extremely long-lived objects. Otherwise, you just have to say that they're not really fat volume filling things, which is what I would argue. I mean, there are very few people, I think, who would go out here, who would really go much past like here on the lifetime anyway. So I think most people would say like, okay, great, they're not reacts, they're not volume filling fat things. And then if you throw out that 30%, then you can constrain the lifetime of the rest of them using this tactic. Yeah.
And so are there observational constraints that we can put on here, which are other estimates on how to measure the duty cycle?
Over like 2, 3 orders.
That's
of
what
magnitude.
Sorry, yeah.
Yeah, 2 or 3 orders of magnitude within 2 or 3 orders of magnitude.
Right.
So it'd be a fat bar.
It would be the width of the plot, right? It is. That's why I made the plot that width. That's why I chose it to be that width. So that's my exactly right. LIGO can better constrain the lifetime of AGN today than EM signatures.
But isn't the problem that you have other channels as well? So you could have.
Yes, you could have other channels, but the thing is that you can't have. So I'm just looking at this is the LIGO upper limit, right? We don't live in any universe on this side of the line. All of this is strictly forbidden, even if you believe that every single LIGO event came from an AGN. So none of this parameter space is permitted. All of it is forbidden. And if you additionally go with like 99% of the community and say that AGN, that liners don't actually live even this long, then you're basically saying liners cannot be fat volume filling accretion flows. They have to be low luminosity because they have relatively low mass, but they can be thin.
But if you assume that you repopulate this black hole cluster or population every, let's say, 10 million years, so you basically bring in 20,000 black holes every 10 million years.
You don't consume all of them, even at that
so
rate.
even if you merge them, they would basically stay in the cluster, right? More or less. Right? They would be kicked out.
Yeah,
So you would accumulate a very large population of black holes under these assumptions, right?
But they can keep merging, right? N is just, and they
But
can merge.
the total mass will not decrease so much. So the total mass in stellar mass black holes under these assumptions after 10 gigayears would be really large, larger than the mass of the supermassive black hole.
No, because that's actually not the case, because at the migration trap, the gravitational wave decay timescale is short enough. It's less than the Hubble time. When you get very massive objects, the gravitational wave decay timescale will have them crash into the central object sooner than. So you're not constantly adding a number n.
You're growing the supermassive.
You're growing the central object yes instead. Yes.
Yeah, I think I would just add. So I would just add. I think Bente's point is a good one. That we're considering the population of black holes in the central cubic parsec, and so we need to understand the larger scale processes that deliver black holes in there, that consume them in there and kick black holes out. And so we have star formation, we have dynamical friction, and so we can say for sure that all of the black holes in the galactic nucleus are not being consumed. Otherwise, we'd have a way higher merger rate than we observe, right? In a single impulse, and so we can already say that the consumption rate over a duty cycle cannot be that high, And that restricts that epsilon parameter that we were talking about before.
Oh, and let me just add, yes, I did not say, and it's not written up there, but the epsilon assumed here is 1. So basically, whatever you start, if you start a cycle of activity with some number of black hole, stellar mass black holes, you are assumed to start the next one with the same number of black holes. But the results for this don't change substantially unless you really crank down epsilon, right? So you start each cycle with a substantially less black holes or substantially more black holes, and then you start to get into problems, right? So it's a question of how many you consume per duty cycle. Yeah. So that's my, yeah. Okay, yeah.
So the Milky Way was an AGN, right? Not long ago, apparently. Is there any? Yeah, right. So if one of these things go off in the Milky Way, what can I expect on Earth? Can we maybe link some extinction event on Earth history to it?
Sorry, do you mean what happens if an AGN goes on in the center of the Milky Way, or what happens if a black hole merger
goes on
happens?
in the Milky Way? How would it? No, yeah, sure. I mean, the column density is high, right? But a major one, say like mass ratio, I don't know, 10⁻². So.
I mean, we don't. I mean, the thing is, right? We don't know that there are any electromagnetic signatures of two black holes coming together. So there would be. I can't guarantee you that there would be any electromagnetic signature at all, and the gravitational wave effect.
Oh, GRBs or something.
If there's GRBs, I think people have looked at GRBs.
GRBs.
No, there's neutron stars, right? So
But for black hole, major black hole merger isn't going to produce a GRB unless you can somehow make the disks do something funky.
Can we just say exactly what we mean by major black hole merger? And what masses are you exactly?
I
You
think
mentioned
Vlad
the
is
mass
like-
No, I
ratio
think like
and
at the
the-
top of the distribution. Imagine that you are, you are done with the black hole infinitesimals, and you are on the
10,000
black
of the
hole
million.
embryos. So mass ratio maybe, like.
Yeah.
but if it's only a gravitational wave
Oh,
signature,
sure, yes, that's just going to be waves going up and down. But GRBs, that would happen in the
1%
AGN.
of the
but there's no, so the GRBs would only happen if there's a pair of neutron stars,
Right.
which you might also expect to happen. And I do think that people have looked at like what sorts of bad things happen if a GRB happens near enough to you, and like I think somebody calculated there's like a neutrino kill radius, like you'll die from the neutrinos alone if you're close enough to a GRB, and I forget what that distance is, but it's not
Very
like,
short.
but it's not 2 centimeters short, it's like, yeah.
Parsec or something.
Yeah, it's something, I don't remember what it is, but it's like, it's,
Right.
short
But
and,
then
short and astronomical
Yeah, but
terms.
then my other question is tied to that. Is that this channel depends on AGN, right?
Yeah,
So there shouldn't be any strong correlation with redshift.
there is,
With-
there should be. There should be a strong correlation with redshift for AGN, because there is
More
a
AGN in the past than.
Yes,
now? All
right,
okay,
it peaks
but-
around Z of 2.
Right, sure, yes. But in any case, the other channel, I would call it the competitor channel, would be the primordial black holes, right? Well, POP3. POP3 stars, there should be a strong dependence with redshift. Is that
Yes.
something that can be tested observationally?
Yeah, I think the first day,
Go for it.
on Monday, we made a list of observables, eccentricity, spins, masses, and I think one of them that was suggested to put on there was redshift distribution. So I think it is an important thing that each channel might have a different prediction for.
And I think, as I understand it, that the redshift distribution prediction is not so straightforward for the field binaries, because there's like, arguments that there's low metallicity gas locally and that can, I don't know, you say more.
Yeah, so in order to correctly predict a redshift distribution, you need to understand the metallicity distribution of all star formation history in the universe. And the delay time distribution from all binary compact objects that you form.
You want this?
For predicting the field, the cluster, I think it won't be as bad, but it's still also pretty rough. So my sense of things, the AGN, would you be able to get more prediction for that, but to disentangle it from the uncontrolled bias from the redshift distribution of the field formation channel would be tricky. And I think the better way to do that there is to pull out distinctive subpopulations that are clearly from an AGN subchannel, and then get the redshift distribution of those. It was much easier to do. And you also get better measurement errors and all sorts of wonderful things. But yeah, using the redshift distribution is really hard. I mean, you can measure, particularly in future trajectories, exquisitely well. The problem is you have no idea what it means.
Well, you might want to combine it.
Yeah, if you combine it with other, yes. Yeah, I mean, yeah, but it's correlated with all these, it's correlated with extrinsic properties of the universe that are input parameters for your binary evolution code. So it depends entirely on how well you measure other things that are really hard to measure. So you need not only the mass metallicity relation, but you also need the dispersion of the mass metallicity relation, and you also need to do it in substructure in individual galaxies, while also resolving the contribution of H1 disks over cosmic time.
I only have one ansatz, just.
Okay, sorry.
Kidding.
So it's really tough to do the time to get because there's this, for BBHs in particular, there's this subpopulation that's important, and because our theoretical understanding of things that you can do to tweak the delay time distribution there are ways that you can move it around a bit. You don't want to, the relative contributions of different parts, you don't want to put all your eggs in one basket when it comes to that. That being said, there's a lot of people working on cosmological hydrosimulations, and you can populate the universe with your favorite, so there you have no uncertainties, you know exactly what you put in, you can come up with predictions, and if you do that enough times, I might be wrong, and maybe there is some more universality in the redshift distributions than I would have expected, but my sense of things is the normalization is awful. That's hard, and the delay time, the shape is also rough. So I would do other things first, because also measuring that to get the shape means that you have to reach out for a while. So it's probably not until 3T until you really get a distant shape. You're just going to see it goes up or has some slope early on, and everything does that. So with ET you can do everything, but you'll have also done everything because you'll have 1 million events a year. I mean, come on, you can do anything with that. So we'll know everything exquisitely then, and by then we'll also probably have better infra physics. But for now, I personally would put my efforts on lower hanging fruit. Sorry, long negative rant. I'm sorry.
No, but and just actually so that I'm clear on this, especially with the improved reach, or maybe Zsuzsa has, but how far out in Redshift are we going to be getting with all of the wonderful upgrades that are definitely happening?
Yeah.
You mean A+?
Yeah, and yeah.
G is equals 10.
What?
The third generation of formers are binary neutron stars is equals 2. So I mean,
Oh.
3G
So
is
you mean all the way into the future?
No, I don't mean all the way. No, I mean like in the next 5 years.
Oh yeah. So yeah, then
Well,
That's not the future.
That's what we're living tomorrow.
I don't know the answer right now.
actually, do you know the exact answer right now? I'm asking you.
I can pull up so.
That's the problem. We are always thinking of BNS ranges. So that's
So
I
take
guess that's
170749, which is the redshift. Take 170749 and multiply it by a couple. I'm asking someone to look up a table whose number I should know. It's redshift of 0.4 and then multiply by a couple because we can see farther.
Yeah.
So
1.2.
yeah, 1.2.
yes.
Okay.
So not to redshift to for sure.
Yeah.
Much
But over
below.
redshift 1.
Good.
Okay, so what mass This is advanced LIGO.
Oh, that's the Astro paper?
This is
And
the-
it's mass
Oh, yeah,
dependent.
this one.
Right, of course, it's mass dependent, but I guess the most massive thing, I mean, and that, well, yeah.
I
Yeah,
think
about
we
two.
do have a
This is
30
equals-
plus
Do you want to
34.
replay that? or-
Zeke is two.
Yeah, can you
Yeah.
replay it?
Yeah.
Z equals 2.
It's not a
You
max.
know how to do it?
It's not a math,
You
you
just
can't
want
do
to-
it. Oh.
Oh, it's not math, okay, yeah, sorry, can you look at the plan?
So extra.
I can just draw the.
Yeah, okay.
Yeah,
Drawings, please.
yeah, he's working on it.
Oh, yeah, you can erase that one. Go ahead, do that one.
Here's the mass. Each set something like 100.
Yeah.
Oh.
That is so low.
10. And goes up to. Oh,
There you go.
thanks. So this is the horizon redshift, and at 100 it goes to something like 2. But this is a log scale, so this may be much less, 0 point
Do
something.
you want it at 10 or do you want it at 1?
At let's say 1.
At 1, it's about 10, 20, 30, 40, 50? It seems small.
50 what?
Oh, no, sorry, point of redshift.
0 point.
0.235? 0.05.
0.05. Yeah, and then it cuts off. And so, but this is just the horizon, right?
Yeah.
And let's say the 50% confidence is like a.
Factor of 2.
So I think it goes to redshift of 1 or something.
Yeah, it goes to redshift of 1.
And this is the advanced LIGO design sensitivity, but A plus goes up to redshift of 10 or something.
It's a factor of 1.5 in range and 7 in volume. So I would do 50%. Susie, if you want to call it like that.
It's in that plot. No?
No, that's CE, not.
Oh,
not
that's
A+.
CE.
Yeah, so Z equals 10 is C is.
This is
CE.
Cosmic Explorer.
So this is, yeah, so that you'll only go up to Z equals 3 or so.
Okay.
So, sorry, not Z equals 10.
That's good, it gets 2.
Yeah.
Which has to be.
Okay.
Yeah.
Yeah, as long as we see the.
3 is
Brother.
greater than 2.
Yeah.
On the last
Some
afternoon, I'm
universes.
so glad I figured that out.
Actually, it's in the LIGO indicator.
Oh, it's in the Decadal too?
Great.
Okay, good.
So, which is just was
Which is-
yesterday, yeah. I said I have a graph, but
Okay, cool.
I did not.
Cool.
use it.
Nobody.
That's
Um,
back on.
Okay, yeah, we can hear, we can pass it up here. So I think nobody, oh. Is it
Yeah,
from
it's
there?
Amy,
three.
turn off your mic.
Is that it? Okay, whatever it was, that's better.
Okay, maybe it was my mic. but
Sorry.
You're not showing muted.
Oh, that's because I didn't even set the audio up to work on my laptop, so.
Oh, okay, it was my fault then.
That's why it would be
Sorry.
weird.
Okay.
I was even looking at it, I was like, I didn't read your permission.
So I think, so unless other people have sent me slides, did you say, or?
I just had a question to pose if we're gonna move on.
There's one more thing that I want to show that is, because Imre is not here, and I think that he showed this on Monday, but I want to make sure that it gets emphasized, because I'm not sure that, he had a lot on his slide, and I want to make sure that this gets, escape, okay. Where is it?
Just back out of that.
Back out of the, okay.
No, no.
I don't know if that's in the downloads.
Yeah.
Oh, you don't think it would? Let me try.
Yeah, Monday, yeah.
See you on Monday.
Oh, okay, you got it.
I know where it is.
Okay, but
I
that's
think.
on the, that's not downloaded. That's downloaded.
Okay, but if it was,
Are these Emirates?
these are, this is actually, yeah, so, Lindsay had put everything into one, so I just need to go down.
Quick review Monday.
Here we go. Yeah, this one. Okay. Good. Well, yeah. Oh, that's on Rainier's slide. No, no. Yeah, that one. Okay, good. It's basically think it's only slightly different, maybe the same graph. So just in terms of observables, since I think it should just get brought up in the context of observables, and with Richard commenting that, we'll have 1,000 very soon, that is a great number. And that is because we can do this statistical game, right? If you know what the background density of AGN is, and every time you go as LIGO and you have an extra AGN in your error box, is sort of the way that you can think about this, then the first time you do that, well, it's just statistical noise. The 10th time you do that, it's noise. The 660th time you do that, you go, wait a minute, there's too many AGN popping up inside the LIGO error box. And so Imre and others in this room showed in this paper that basically these curves are the number of LIGO detections you need to say at with 3 sigma significance at 95% confidence what fraction of the LIGO events are coming from the AGN channel. This assumes that, for our purposes, going back to Dan's question, what's an AGN? This assumes that an AGN is an electromagnetically emitting source, and not just a gas disk that is otherwise quiescent but totally messing up orbits in the nuclear star cluster. But let's go with that. And then this is plotted for various background densities. So basically this translates to what are you counting as an AGN? And I would say that we unfortunately probably want to count the 10 to the minus 4. That sort of includes all the Seyferts, which are plenty massive enough to mess with orbits. So you do need a fair few. So here's, or at least before we had this meeting and I talked to Richard and Juja and everybody, what I thought was like a lot. And that might take us a while. And I've learned that we won't have the answer in 5 years for sure. So here's 100 events. And assuming that the AGN are responsible for all of them, you're sort of in here, right? If you assume that AGN are responsible for about 30% of them, then you still need like 1,000, which is like so terribly soon. So terrifyingly soon. Yay!
I want to add to that, but this was mentioned. Sorry.
There's a mic.
It's actually here.
Yeah.
I want to add to that, and if you could go to the Corley slide, which is basically along the same line. And I know we discussed it on Monday. That we gain a factor of 3 by using the inclination, which we got from the BBHs. I understand this is not easy to tell about the AGNs, but if you guys could think about that, how to beat that.
A few years. You're telling me we might know or 3 months earlier. I'm not going to kill myself for 3 months.
Or we will just be patient, but yeah. But there is another way to go around it, because my take on it is that we can start, although we didn't think too hard on it, but we can start cherry picking some of the best events.
Yes.
Best reconstructed ones, for which we know the inclinations incredibly well, and maybe for the AGNs as well. So that may be the better way to go. We just did not work that through, but that's a possibility.
No, I mean, I know, and you probably might say more about this, but yeah, these results are basically dominated by the best localized incidents, which are not, and this is just for standard, but this is just for standard LIGO localization, right? So we're still having multiple AGN per error box, but few enough that you can notice the overdensity, and so.
These are advanced LIGO design. Localization 3 detector cases,
Yes, but if you have
we gained quite a bit on the distance. That's where we are gaining actually.
Right, and the inclination. The inclination is buying you the distance, right? Because it's degenerate. Yeah.
Yes, that's it.
Okay. Yeah. So that's definitely very so. I think we can be very optimistic, assuming that the gas disks actually shine and are therefore identifiable in surveys. And I should say, I'm not 100% sure about this one, but I think in the original plot, it's assuming like maybe 90% completeness and 0% contamination, something like that. Which we don't actually have any catalogs that look that good, but we have Galaxy catalogs that look pretty good. And so if you just go out and you take the WISE correlation, then you can you can put together an AGN catalog that's 78% complete and 95% clean, or 5% contaminated. And when you fold those numbers in, it does make things a little bit worse, but which was worrying me until I talked to you guys, and you're like, yeah, whatever, just wait 3 more months and you'll be fine. So in pretty short order, we'll make up whatever we need to from the contamination and incompleteness, I think. Yeah, okay, so I think that's everything. Did you want to put up your burning question slide, or?
Meh.
No? Okay. All right, so Dan.
Actually, one question on this, and maybe it's in the paper, sorry if I didn't see, but we're talking about how do you know the inclination on Monday, I believe. Maybe this is a question for AGN experts like Chelsea. If you see type 1 versus type 2 AGN, meaning just obscured versus unobscured AGN, which the idea is, line of sight versus not line of sight, does that give you a factor of anything, even if you believe, first of all, would you believe?
Regret to inform you, I mean, you could certainly argue with this, but I would say that because we actually see individual objects literally changing from type 1 to type 2 and vice versa, that although there clearly is something to do with inclination angle in some cases, I would not rely on that, like, for even half a thought. Oh, you want to?
Yeah, I would just add. Yeah, I would just add that for the type 1, type 2 thing, you can find AGN that are X-ray type 1 and optically type 2, which again, we talked a little bit about this, that may correspond to a warped disk, right? Where the innermost disk is facing towards you, but then the bulk of the disk is warped away from your line of sight, right? And we should expect that in a bunch of cases. So that's why inclination is a tricky problem, especially if you're looking close in, right? Yeah.
The observations of AGN disks that have masers where you can get the inclination really close up show that there's totally no correlation between galaxy disk orientation and AGN disk orientation.
Yeah, there we go.
Was there a so?
Oh, actually, I just have a question.
Oh yeah, and then yeah, so this was the, yeah, so you said you wanted to.
Yeah, it seems like it's maybe come up a few times, but I feel like we haven't discussed it, or I don't know anything about it in the literature. And what do our predictions for the merger rates in the AGN channel, how are they tied to the tidal disruption rates? Because the same processes are going on, bringing stars and black holes into the disk, bringing them towards the central black hole. So is there a connection at all between the TDE rate and this channel's merger rate?
So, let Mordecai say first.
So one thing to bear in mind is that the migration rate is dependent on the mass, and so only the most massive stars are going to be moving as fast as the black holes. So the TDEs from smaller stars are not going to be strongly influenced by the disk.
So I would just refer to the point that Haggai made very briefly before he went out, right? He's saying that, so think about the standard sort of lost cone delivery of, your TDE type events. Now you're putting this dynamically cooling system right in the way. What happens? Great question. Someone should work on this, right? It's going to trap some of these objects. Some things are going to be blocked from making that, essentially the orbit's going to change in a funky way. So you make it funky kind of TDEs. Erin could have talked about this, but she's just gone. Don't. But good question, yeah.
Other things we've missed. All right. Is there something else? No, yeah, okay, yeah.
And this is just, again, one of the polarization, and I have no idea how that would affect things, but I mean, that's one of the things that an AGN is something that has revealed things, but it's very difficult to do, so people don't pursue it. But if there's any impact on polarization, then this is maybe something that may bring that back into vogue.
Inclination angle of the disk.
Yeah.
That is a way of reasonably measuring the inclination angle of the disk.
Yes.
Polarization.
Exactly.
Yeah, because it's a scattering screen. So basically, if your disk is edge on and you can't, well, here, I'll do the thing. Yeah.
Sorry, oh yeah.
So yeah,
I can hear you.
Yeah, that's an excellent point. So yeah, if the disk is edge on, but you have a kind of scattering screen above the disk, so that all you can really see is the scattering screen, you have radiation that's traveling up and being scattered out towards you, so it tends to be polarized. So, I mean, this is one way in which we can explore the interiors of type 2 AGNs. So we know that the bulk of the disk is kind of edge on to us, so polarization can be used to at least gauge the gross inclination angle. Yep.
Yeah. Damn, the white papers are already due. All right.
Do you want me to, like,
Yeah, so maybe.
Jill, the slide you had?
No, I was just kind of summarizing stuff from the morning. It wasn't.
Okay.
So
It's not important to keep.
I can start to do my thing. We can.
Yeah, so maybe what we'll do is, Barry was going to present what we want, so this is like where we think we'd like to be in the next 2 to 3 years. And so maybe from this list, people will discern that there are things that are missing.
Yes,
So we'll see.
Yep, that makes sense. There, it's here. Fabulous. All right, so firstly, folks, thank you all so much for coming along to this. It's been really cool getting a whole bunch of people into one room. I hope you've enjoyed it as much as I have. There have been so many interesting ideas banging around. I can take this opportunity to thank everyone who came. The SOC, who chaired the sessions, did a great job running things, keeping the conversations going. So thank you all so much to make this really, really work. So yes, right at the beginning of all of this, if you remember, I introduced two hats, right? So we have the optimistic hat, we have the pessimistic hat. And I introduced those in the context of the rates that we expect from this channel, right? So if you expect a really high rate, you wear the Yankees hat. If you think that the channel is basically insignificant, you wear the Mets hat, okay? What I want to persuade you of, and I hope that you've gotten from the discussions that we had, basically, let me do this properly, there we go. If you think this channel is not going to be a significant contributor to the LIGO rate, what you're actually saying is you are being optimistic about what we can learn about AGN disks. The whole point of this is that LIGO will tell us more about AGN disks, arguably, than light can, right? That's really, really cool. And so it doesn't matter what you think the rate is going to be. If we can constrain it, the more we can get this, the more we win, right? So we win either way. And so Richard should be doing his happy dance.
But I really want to have some gravitational wave sources too.
We're going to see some. But, you know.
That's what I'm sure.
Yeah. So I hope that you understand that we're all optimists, right? This channel is going to be incredibly fruitful, regardless of the rate that we end up with. We're going to learn a ton, right? And so as long as we walk away with that, I think we're golden. Okay, so to that end, rather than looking ahead to Lisa, or that far ahead, or to even to the massive upgrades, I've just sort of written a bunch of things that we can expect or we want to happen in the next 2-3 years, all right? I think these are reasonable asks. I think a bunch of the people in this room can definitely, collectively, do the stuff that I'm asking for here. So first thing, we want chi-effective mass ratio and eccentricity predictions for this channel so LIGO can directly test this, in 03 and going forward. The first distributions of these parameters that we're going to get are not going to be correct, but they're going to give us a sense of how the distribution probably works, right? And as we learn more from improved numerical experiments and further constraints, we can iterate on these distributions going forward, okay? The development of unique signatures, I think, is a really key thing. I think we have a lot of smart people in this room. I think collectively we can come up with some more smoking guns, depending on what we think is going on. We already have a few, Bence, I talked about a few. So we're looking for these unique signatures at the Agm Disk channel in gravitational waves and electromagnetism. And I think a bunch of people have a bunch of ideas. And so I hope to see some more papers on this sort of thing going forward, right? These are things that will really help us win faster. We'll be sick of winning. No. So in the case of simulations, I think one thing that I think is important, and people can add to these points sort of when I've gone through. In simulations, I think if we can isolate cases where we think the eccentricity is definitely being driven, that is something that LIGO can deal with right now and can tell us stuff about right now. If we can converge or concentrate on what it says about an Agm disk, that you could generate such an eccentricity, that is really helpful. If LIGO doesn't see such a thing, then we know that Agm disks don't have those properties, right? So again, we can sort of push down.
So by eccentricity, you mean eccentricity of a binary about to merge?
Of a binary about to merge, yes. What Richard and the gang are going to see. Yeah. So I think that's something that we can reasonably push on in the next 2-3 years. I mean, I don't know what hat Andrew would wear for that, but I think it's something we can push on. Something that several people mentioned, Dan mentioned it, Brian mentioned it, Hagai mentioned it. We can definitely make progress with sort of thermodynamic studies of Agm disks. If you take an Agm disk model and you drop n objects into it, that's going to have an effect on the disk, right? So we need to do sort of semi-analytic work, I think, to sort of model what happens to the aspect ratio. How much does the gas puff up? What happens to the...
Don't you first need to have an Agm disk model that even addresses the questions we're asking?
You need to start with a model of a model of your Agm disk, and then you need to estimate, or you need to try and get at, right? What will be the impact on the gas distribution if you start dropping n objects into the disk? Where's the mic? It's up there. Oh.
So just drawing on our usual protoplanetary case, Vlad and me and student did some models to see when can a protoplanet start impacting its parent disk.
Yep.
And the answer was you had to get up to 10 m Jupiter, so that's 10 to the -2. So maybe an M-ray can do damage to the disk, but I don't think a bunch of little stellar mass black holes are going to do very much.
But think about it. So one of the questions we want to understand. One of the questions we want to understand is what's the thermal capacity of the disk?
Yeah.
If grind down is efficient, and we end up with a large fraction of the nuclear star cluster in the disk, you're going to blow the disk apart, right?
Then what's the integrated mass?
Right. That's
Yeah.
That's a good calculation too.
Answering that, so what we did, I mean, like what Mordecai is getting at is that what we did is that we put an orbiter in a disk and then we measured how much energy you get from the shocks, right? And that indeed only happens for very high mass planets like 5 Jupiter masses or 10 Jupiter masses. So that's about mass ratio of 5 times 10 to the minus 3. But that was for circular orbit. Once you have eccentricity or inclination, you will get more energy from it, even if you have lower mass ratios. It won't last too long.
Well,
but I mean, right? So.
Yeah, I think the big issue is, right, that the total mass of the nuclear star cluster is likely larger than the mass of gas in the AGN disk, or at least comparable.
In the relevant volume?
Not in the relevant volume, but in total. But the point is, right, that sets up a possibility. There must be some equilibrium. And actually something that is maybe a little bit concerning, right, is we could set up a gas disk model for an AGN disk that has nothing in it, that has no objects in it, right? And we could say this is a lovely and self-consistent disk. But if you have so many objects passing through it, stirring up shocks every time they hit the disk, even if they don't individually hit it very often, right, they can change the thermodynamics of that disk in a way that is important. If you are forming enough binaries and you're always asking the gas disk to take away the excess energy so that the binary can be bound, then, you know, if you do that enough times, obviously there is some limit, there is some maximum capacity of the disk. And so because the total mass in the nuclear star cluster is larger than the mass in the gas disk, you have to figure out what that point is. And maybe there is no appropriate AGN gas disk model in the absence of objects, because if you go and you look in our own galactic nucleus, you expect that there are objects. There are objects that would be inside of a disk. So you can't exactly really. It's not fair to model it all by itself.
What's really interesting, I would actually build on that. So yes, and if you start off with a thin disk, so there may be some sort of AGN evolutionary sequence, right, where you start off with something that's relatively thin, but if you get more and more objects into the disk and you sort of puff it up, there may be this point where the disk essentially dies because of overpacking, right, with grind down. So that may be a cool way of ending AGN. So again, this is all part of this.
Quasar killer?
Yeah, right? So you'd have a sequence of sort of AGN phases from just thermodynamically overloading the disk with grind down. That would be a really cool way of killing these things, right? Someone should write a paper on that. So, you know, but these are things that we can do now, right? To sort of see what sort of predictions we can make for both AGN disks, but also what LIGO can help us with, right? Sort of related to that, I think another point that I sort of got from a lot of what people were saying was phenomenological modeling is also a really cool thing that we can do now. What I mean by that is, if you're interested in you know, what happens when a stellar mass black hole comes in as an emery towards the central primary object, and you disrupt the inner disk, that is going to show up now. We will be able to detect that now, right, in the EM. We'll have to wait for LISA to get the gravitational wave signature, but we should be able to. It is not beyond the realms of the next 2-3 years that we can put together a reasonable model of flicker around the ISCO as something plunges through the last few orbits. And so this will help build towards LISA for EM signatures, but it's also, it guides sort of large optical and UV surveys, right? Things that we are doing now, things that we're sensitive to now, right? And so we can at least constrain the rates of memories that we might expect from this channel for Lisa. What else am I saying? Yes, serendipity. I sort of included that at the end. So we're going to get 50 black hole merger events in the next year. What are the odds that they're all going to be boring? Come on. There's gonna be one where people will go, "What the hell was that?"
Even the dance
right?
is exciting.
Yeah. There's gonna be one that everyone will go, "What the hell is that?" Right? Those are our lever arms. Those are the things that will go, there's something that we can attack here. That's gonna happen in the next year. Our serendipitous stuff kind of on the EM, I think, we're talking about those weirdo events in AGN disks. Supernovae, tidal disruption events, GRBs. Right now, something that people haven't really thought that much about is the fact that while we haven't observed that many GRBs, I think the long GRBs, there's no connection between those things and AGN disks. We should expect GRBs and AGN disks if this pathway is remotely efficient, right? So why don't we see them? What happens when you blanket a GRB with content-thick gas? That would be an excellent paper for someone to write, right? What's the spectral signature of that? Maybe we are seeing those. Maybe we're not. I'd like to know the answer, so someone please help, right? We're going to see TDEs, supernovae, all sorts of things in AGN disks. So for our observer friends, anything that's weird, yeah.
How are you going to see any of those in an AGN, a bright, optically thick AGN disk?
So that's let me rephrase. These events will occur in AGN disks. The question for our community is, what will those things look like? What are the signatures that we should search for? I would argue that there should be associated low angular momentum gas that will result from these events. And so there should be an associated spike in accretion, a delayed spike in accretion. But it's going to be complicated, right? It's going to depend on the assumed turbulence.
Well, you need to have a mass of low angular momentum gas that's enough to overwhelm the inner disk so it doesn't just slam in and get stuck there.
Yeah, that's right. Yeah.
Tall order, it sounds like.
So it depends where it happens. Yeah. So this was kind of my back of the whiteboard sort of sense of things that we can work on in the next 2-3 years. So if we come back here in 2-3 years, I would like to see this level of progress, right? I think it's not too much to ask. I think we can do this. What am I missing?
At some level, these are macro scale requests, but they require a lot of micro scale development. For example, just number one, to get a distribution prediction, you need to know more about AGNs, you need to know more about nuclear clusters, you need to know more about how objects from the nuclear clusters in the disks move.
Yes.
Those 2 to 3 years seems very optimistic to me.
So in a couple of weeks, we will hopefully have the zeroth order chi-effective and Q distributions for various assumptions about exactly those things up on the archive. I think we're relatively close. But basically, yes, so we can then test. So depending on the distribution of these things for various assumptions, gross assumptions, zeroth order assumptions, I think we can start to assemble these sorts of things. Zeroth order, yeah. Carl, yeah. Oh, there we go. what to add.
So it's actually just a subset of number one, but the correlations between those things I think are where we're going to get a lot of the more interesting physics. In particular, the correlation between chi-effective and the total mass. So there's several formation channels out there that allow you to multiply merge black holes and then build up things in the pulsational pair instability gap. But with all this gastrophysics mucking up the accretion onto these things and the spin parameters, I think if you could, for instance, see something in the mass gap that has a spin significantly different from 0.7, that, to my mind, would be, if not a smoking gun, at least highly addictive.
Remind us what mass gap is?
So the pulsational pair instability mass gap, so there's two mass gaps, right? There's the little mass gap between neutron stars and black holes. That's around 2 to 5 solar masses. And then we think that above about 50 solar masses, up to about 150 solar masses, give or take, you don't get black holes from single stars, because essentially any helium core mass above about 50 solar masses will undergo these pulsational pair instabilities. Basically, you get such a ridiculously high energy pressure of photons that you begin to pair produce electrons and positrons. The photon pressure in your core vanishes. Suddenly all these positrons and electrons recombine. Your core suddenly... and then if it's big enough, you'll actually get a massive one of these and a single supernova that we think does not leave behind any sort of remnant. And so there's been a pretty good argument that people like Stan Woosley have been making for years, which is you just won't see black holes from stars in that mass range. And so people like myself and Fabio have been saying for a few years now that if you do see something in that mass range, it's at least indicative, and it has a spin of 0.7, then that's indicative of a second generation black hole merger, or a third generation, where you've merged multiple black holes together and produced a new thing. But, I mean, if you have all this gas accretion happening onto these objects and torquing the binaries, I can fully see that instead of producing this nice, clean, like, GR-related peak at, say, a mass ratio of 2 to 1 and a spin of 0.7, you could get all sorts of weird chi-effective distributions and individual chi distributions. And that, I think, if you're going to do that and you need a large amount of gas to do that, that pretty much puts you in an AGN. I can't think of any other formation channel that has that much gas mucking up your clean dynamical picture.
That's right, yes. So in the stuff that we're working on, myself and Savik and Richard, yes, you will mess up the chi-effective distribution, for sure. Yeah, I did show the plots, yes. I didn't explain them, but...
Oh, well, that might help.
That doesn't count.
Yeah, sure, yeah.
So is that similar to saying that if you have a channel or 2 channels that we think we understand the predictions for these parameters pretty well, and a linear combination of those 2 doesn't... So we get observations, and a linear combination of those 2 predictions doesn't match the observations, and the leftover could be the AGN channel? So we don't have to make any predictions for the AGN channel, we're just looking at the residual? Yeah.
So you mean we take apart all the ones that don't have 0.7 and everything that doesn't have 0.7, we just say was formed in an AGN?
Yeah. So then we should be trying as hard as possible to come up with...
No, hang on. No. We have to show that we can do it in an AGN before we can do that.
Oh, we did. Well,
Yeah.
Tell us more.
Yes.
Someone give him a mic. And someone give a person a mic.
Talking? I don't know who's
we're
talking.
doing it to him
who's talking?
first. Somebody.
You.
Richard.
Okay, here, yeah.
Very
Okay.
confusing.
There we go, complicated exchange.
Convergence.
Yeah, go on.
Yes.
Could you explain the letters in that?
So this may have gone by because I also did not explain my plot. But one of the figures that I had in my plot, and I'll come to this in a second, was one of the things that we do is try to pull out generic phenomenological guesses as to what the data actually tells us is really out there in the universe. You see enough things, you can say, oh, there's 2 groups of TRBs. Or, you can classify galaxies into multiple groups and say, okay, they're phenomenologically, even if I'm still trying to work out what's really going on, I can see with, my few thousand events, oh, there's different classes. And you can do that in mass and spin and redshift. And so the data will tell us what's there. And for a scenario where you have a very clear, strong interactions in assembly, as Carl has pointed out, as we have it in this, you get very specific trajectories in mass and in spin, and you'll get very specific predictions for what the chi-effective distribution will be, and you can start to pull these things out. This isn't about mixtures per se. This is more about what would the predictions not doing the subtraction would be. The mixture is a separate question, but the masses are so characteristic for the field, and they don't do things, as Carl said, that the Agm disks do. And the clusters, similarly, have very specific predictions, particularly if you get hierarchical growth, these spins of 0.7 that you tend to produce, which you would not get here. So it's difficult to completely confuse the two, and then and you can begin to pull these things out because you have certain constraints on what the shapes of certain things have to be.
Yeah, just so if you can't quite read, this is number of events. This is chi-effective from -1 to +1. We have mergers in the bulk of the disk. We have mergers at a migration trap. And
how are you deriving those chi-effectives?
Monte Carlo.
So this is Monte Carlo simulations.
What assumption?
Okay.
We don't. Yeah. Okay. Well, he's not.
So Serco and Goodman disk. Initial population of a few hundred black holes embedded in the disk. For this one, we assumed a IMF between 5 and 50 solar masses for the black holes, with a index of 1, I think, for the one on the left. We picked from a uniform distribution of spins, so anything from minus 0.98 to plus 0.98, so random orientations compared to the disk angular momentum, and so you can measure the chi-effective of a binary that merges, assuming that a Barreau prescription applies to the binary for the merger.
Whoa.
So lots of assumptions, but but that's what I'm saying, right? What we're trying to do is the 0th order initial distributions for LIGO from this channel. Yeah, here.
And I mean, I think the big point, right, is that a lot of people have been looking at the chi-effective and that have come out of the first 10 mergers and said, well, it's low spin, it's low, everything is, and the point is just to show that there is a scenario that is plausible within the Agm disk scenario that gets you perfectly consistent results for chi-effective mergers happening in an Agm disk. Am I going to, bet my firstborn on this? No. But it's not beyond the realm of crazy to say it basically does show you that for some maybe not totally plausible but also not totally crazy assumptions, you're not always going to get these 0.7 2-to-1 in this scenario. And I think, like, to elaborate a little bit more on the conditions, right, what we did was just say that you're going to throw these objects down randomly, you're going to apply the migration torques appropriate to Serco and Goodman, and you're going to allow them to find each other, and then they'll merge. Yeah, you're assuming a pretty rapid merger thereafter, but you're putting not a crazy number of objects in, you're putting them in a not crazy disk, subjecting them to not crazy torques, and you're just assuming that their initial spin distribution is random, and you do allow the spins to change by mass accretion.
Yeah.
And the only other thing that I think is probably an important assumption in here is that we assume that half the binaries form prograde and half the binaries form retrograde, right? But so those are, I think, the critical assumptions that yield distributions that look like this.
Right. So there's a couple of important caveats. In fact, half of the paper is caveats. Yeah, you said that's right. Okay. Here's what we're assuming. Here are the things we're ignoring, which is appropriate. So we're ignoring, for example, tertiary encounters. They're going to be complicated. There's going to be fun dynamics that will add a layer of complexity to this. You know, what we're doing, as I said earlier, is sort of making the first gross adjustments to our models, right? You can test, for example, if you turn grind down off or put grind down on and see what sort of difference that makes to your gross chi-effective distribution, right? If you assume a different spin distribution, you can tighten up the end chi-effective, right? So if you assume that all the black holes in your IMF have low natal spin, or maybe they were all spun up to a given alignment by a previous AGN episode, then maybe you're selecting mergers from a much narrower range of spins. You end up with these tighter chi-effective distributions. So you can kind of play with, you know, gross parameters and see what sort of effect that has on your chi-effective and mass ratio distributions. You can also change your disk model. So we also go from Serkin-Goodman to a Thomson-Quadrant-Murray model. You can turn off the migration trap. You can say, okay, what happens if you don't have a migration trap? In that case, you find that your upper mass limit is something sort of for, you know, zeroth order assumptions, probably somewhere in the region of 80 solar masses. So maybe LIGO's upper limit tells us something about the existence or not of migration traps in AGN disks, which tells us something about the density profile of gas in AGN disks. So this, again, is another way that this turns into this. We are all Yankee fans in the end. The Yankees always win.
Let's not go overboard.
Just saying. So, yeah, problem.
So I had one other thought on sort of smoking gun observables, and this actually goes back to something Savik was saying either today or a couple days ago. So like I said a second ago, we think the only way you can really build up things in the pulsational pairing stability gap, right, is through multiple mergers. But if you do that in either globule clusters or galactic nuclei, anytime you have a three-body encounter and you have a large mass ratio between these things, you're most likely going to swap out the least massive companion. So you're mostly going to build up towards equal mass binaries. And that's going to be true in globulars. The best you can get is maybe 2 to 1 if you have one second generation merger. In galactic nuclei, it's going to be even worse because you'll have a lot of second and third generation mergers. So you'll almost always go for equal mass systems. The only way I can think of creating, basically what I'm getting at is if you see something in the 10 to 1 mass ratio regime and one of those components is in the mass gap, that's AGN.
Yeah.
Like I actually don't know what else could do that.
Yeah. Agreed.
Yeah.
Yeah.
Is that also in y'all's paper?
Yeah.
Okay.
Yeah, so it's a beautiful prediction of this channel. If we get a 10 to 1 the mass ratio, I don't know of anything else that can do this. And if there's a migration trap, you know, you'll get plenty of sort of 10 to 1 type events. Yeah.
Well, it's not clear to me that in nuclear clusters, if you
Mike,
go through.
Mike.
Sure.
You can hang on to this one.
Well, just a brief comment. I mean, in our models, we do get very high mass ratios also from multiple mergers in nuclear clusters. So I'm not sure why would you not get any.
Well, because anytime you have a binary single hardening, right, or a binary single encounter, if you have a 2 to 1 or 3 to 1 mass ratio, you're almost always going to exchange out the least massive companion. So as long as you have 2 second generation or 2 third generation binaries, those are almost always the ones you're going to merge together. Like, I mean, we see this in the only reason, in fact, we get 2 to 1 mass ratio or 2 to 1 mass ratio objects in the globular simulations is because you'll sometimes only form 1 second generation merger at a time. So it finds the most massive companion it can, which is still half its own mass.
Right, but I mean, the idea is that you, after like a couple of mergers, basically you're the most massive black hole that you have formed through repeated mergers is going to always be the one that merges.
Yeah.
Because it's much more massive than anything else in the cluster, and so that will be mostly be growing by creating smaller black holes.
Will it stay in the cluster?
Yeah.
So you need a massive enough cluster to hold on to the.
Like a nuclear cluster.
Right. Okay.
I mean, so in this case, so the most massive black hole keeps accreting smaller black holes, and we find mass ratios.
Yeah, but I'm inclined to think that more likely you're going to have, say, 2 second-generation black holes merge, produce a 3rd generation. Eventually, you're gonna have to like start, sucking up the lower mass black holes. But I think you're more likely to still keep producing 2nd and 3rd generation things that will then merge as equal mass, preferentially equal mass binaries.
We don't find that. We find that, so the one, so there is,
Yeah, Fabio, keep talking, but
no, I mean, we find that there is one black hole that grows preferentially in the cluster while the other ones are, you don't agree with that.
Well, I'm trying to, this was at the semi-analytic stuff?
Yeah.
Does it allow for binary single exchanges?
wait.
What do you mean?
Oh, so now.
I think I understand. There, this is, I think it's sort of the same source, right? In the nuclear star cluster gas-free scenario and in the Agm disk scenario. Once you build up to something massive enough, there is no other partner that is close to its mass range. So every merger is going to be a high-ish mass ratio merger whenever that thing eats something. So I think, but in order to build up to a mass that large, you need to have a system that can hang on to that so it has to be in a nuclear star cluster where you're in the deep potential well. It couldn't happen in a globular cluster where you're going to get booted. Yeah.
Yeah, I mean, what I'm saying is that you're right that you do get a lot of 2nd generation merging with 2nd generation black holes, but then as you keep growing above a mass ratio of 1 to 3, then the most likely mergers are between something very big and something very small.
Right. So could we say that if we see a high Q, that it's certainly happening in a galactic nucleus?
That's
fair.
Okay. I would agree with that.
And I'm actually going to say something else then in light of that, which is that depending on the fraction of galaxies that you want to call an AGN, and depending on how effective gas is at speeding up binary hardening, I think that it is plausible to argue that AGN may dominate quiescent galactic nucleus mergers for the following reason. In terms of the rate. So if the rate depends on the binary lifetime, then if the rate contributed by a quiescent nucleus and the rate contributed by an active nucleus is going to depend on the lifetime of the binary in each nucleus. And it's also going to depend on the number of nuclei. But if they're otherwise identical objects in terms of binary fraction and other things, right, which, okay, maybe that's not the case, but let's assume for starters that they're otherwise identical in terms of important variables like how many stellar mass black holes there are, what is the binary fraction, then the lifetime of a stellar mass black hole binary has to be shorter in an AGN nucleus than it is in a quiescent nucleus in order for the AGN to dominate. But it only has to be shorter by a factor of how common they are. Right, so I can write, if it would probably be helpful if I wrote this out.
Yeah.
Right.
Just flip the board.
A good idea.
Right here.
Yeah, and then we'll stop for coffee. So basically, the rate for quiescent is going to depend. It's going to depend on the lifetime of the binary in that quiescent nucleus, and it's going to depend inversely on it. And in a quiescent nucleus, and it's going to depend on how many quiescent nuclei there are compared to active nuclei, right? So we'll say FQ, and the rate for AGN is going to be the same, but it's going to be FAGN and T binary in an active galactic nucleus. So if you want to compare these two rates and which is going to contribute more, then you can just divide by them. So this is arguably a number we can know, like what fraction of galactic nuclei are quiescent, which fraction are active. Let's say it's 10 to 1, right? So then the binary lifetime in an active galactic nucleus only has to be 1/10 the lifetime in a quiescent nucleus.
Average.
On average, in order for them to be equal. And if this is even shorter, if this lifetime is even shorter than that, then the active galactic nucleus will dominate.
If you get them to merge.
If you get them, so if you get them to merge. But I would say, like,
Are you assuming that there is a steady state distribution? Why is the merger rate proportional to 1 over the merger time?
Yeah.
But that's,
Is this reasonable? I mean, I mean, it's not clear to me that the right equation, the one that you wrote for AGNs, actually is true. That the merger rate is proportional to 1 over the merger time.
well, it's also not true that it's going to be some sort of equal distribution of binaries, because the AGN is also promoting binary formation in a different way than a cluster will.
right, but I would just say, so I'm sort of, yes, I agree with that statement as well. So it's arguably even more the case, if that is true, right, that the AGN are capable of dominating over a quiescent nucleus.
Well,
But
he would perhaps argue that clusters are good at making binaries for various reasons. Sure.
Well, but I would say, right, that nuclear star clusters are good at making binaries, but they're also good at breaking them, right? So a lot of the interactions, you have a binary that forms, but then it's ionized. And so the lifetime to merger for that binary is infinity because it never merges. And that's something that rarely happens if everything is in an organized low relative velocity situation in an AGN disk.
Retrogrades.
Right. So, but in the collaborative spirit of what we're doing here, I think it's also fair to say that if the gas is not efficient at getting the binaries down to final merger, then we have given you, and Carl, wherever he is, we have given you a great seed population of possibly already very hard binaries that can then merge via tertiary encounters. So we would be the catalyst for dynamical mergers in galactic nucleus. So we win, again, we win.
And yeah, I mean, absolutely, just to amplify that, right? I think if you have a couple of stellar mass black holes in an AGN disk and they're a relatively soft binary and they're a binary that would be easily ionized by collisions in a typical nuclear star cluster, the gas, I think it's not at all, well, okay, modulo feedback, it's not super crazy to suspect that the gas is going to initially harden it pretty rapidly, but then you're going to run out of gas, and so then maybe you won't be able to get it all the rest of the way there. So maybe that is where you get a source of hard enough binaries that you can have collisions galore and you're thrilled because it just hardens them some more. So yes, there's absolutely potential for interplay.
So any other thoughts or comments? What else have I missed?
Actually, it's
coffee
break.
Oh, yeah. That's what I've missed. It's coffee. Yeah.
Back in half an hour.
Yes.
Yeah, for just a last round.
An hour to write my talk. That's way more than looking good. Go get me some coffee.
Yeah. Surprise.
I want everybody to
It's just like
even if they're asleep for that.
Can I put this one?
Take a half hour now.
Yeah. Yes.
I haven't really slept properly since like Friday.
I don't.
Is this for no reason or because you're sick?
No, neither.
Okay, that's too bad.
Yeah, I'll sleep today. I have nothing to do tonight.
What's that?
I have nothing to do tonight. I've canceled my plan.
I know. You can trick yourself into
Már előtt, én igazából még azt is elolvastam, hogy mit kell propózolnatok, aztán valami írokos dokumentumot néztem, áttaláltam. Mármint, hogy nem is kell hosszú propózolni, vagy valami igazi
No, but the thing is, like, it's funny because I saw.
Yeah. I think it's ebből a, ja, valami, ami most volt beadva, és igazából az
Nem tudom, de szerintem az van, hogy abban bíznak hogy majd nem fogják annyira mindenki fél. De összességében
Oh, just for me, yeah. I'm sorry, that's good. Alright, next.
There's only one.
Nem, másokat akarnak támogatni.
There it is.
There we go.
Wow, 100 more views since the last time you viewed it.
Well, I'm just gonna. Oh, it's really good. Excellent.
Yeah.
And the handle. Very good.
It's good. And in the end, we even had the little time delay between you ringing down and me ringing down. That was more like, I don't know where this is going.
Now,
So I'm just
like,
trying to
how
figure it
to take into account like the reach and the feedback.
We need to measure your response by.
Igazából a
Okay, great, yeah, because even the spectrum has been exactly. So it can be like supercarbonaceous gray or not.
Yeah. Right. Yeah. So I would kind of like to see. If you could do it in the next half hour, I would call you in. Yeah. You can
Look at that bioform. Nature.
Ugye az elmér pedig az van, hogy hasonló, mint a radiant, csak ez a média valamilyen. Értek ezek a vezetők, tehát az van, hogy ott is azt mondják, hogy lefelezték a támogatást, de 40%.
No, never true. Not sure how it happened.
Yeah. De nem az azt tudom, hogy felvenni,
ez nem, ez van egy... A fej, ez a kis így látom, ez olyan kis ötög a Parkovicsnak a vállán, így egy kis hasonlájával született a Parkovicsot, és megmondja, hogy hogyan szentelizálja a
ennyire, én azt hittem, hogy jobban álltak végre, és ennyi az egész, és nem az, hogy azt hittem, hogy havari alap van, de nem gondoltam, hogy elején befolyásos azon kívül voltak tőle, és elérjük a forrásokat, meg a saját
sokszor, ez csak az volt,
ilyen régi haverizmus.
és aztán fejteket ezt ugye most már az Orbánnál is.
Ennyire
nem meglepő az, hogy hát parkot
If you don't mind, no, it's good. I'm like trying to I'm trying to get to each session, and that's the last session I'm doing. But that's like I think I may just.
Alapvetően centralizálják a hatalmat, és sokat megmenni, hogy mindenki kell, hogy elveszed az intézményeket, akkor az intézmények tudnák és aztán visszalöv a pénz, de csak azoknak az embereknek, és a községek, és olyan soha nem megy a pénznek, hihetet, hogy így az a én nem vagyok lojál, és ezért érdekelt
Én azt hittem, hogy egyik olyan mérges voltál.
De így látszik, hogy nem, mert de most legalább aláírt azt, hogy egyáltalán az intézet befogadja a pályázatot a DMC esetén, amit szintén látszott, hogy azon szintűszor, de az esetén amiben az van, hogy
I think you're right, but I keep.
Is it play D&D and we had a 6-sided die. No, it had 6 sides. You said each one was
Yeah.
3. You could have it 4.
Yeah.
So you cannot have it be satisfied.
Not in our not in our three-dimensional space.
Right.
I've just never actually.
We are limited by our own.
Take whatever.
And I remember there is some like geometry things. There's a number of vertices we had is replaced number of sides by some close to 2.
Yeah.
So that's the even number you have which is the same state.
If you made a cylinder, you could have one that was curved and then one on each end.
So in a geometry version of the universe.
Yeah. Well, I mean, it had the top and the bottom as well. The top and bottom of the wall. Then you
Very much.
hard to look at.
Now I'm in another thing.
Now you can
We
go.
have some discussion.
No.
So, unless you want to talk to.
All right, we have now solved those.
You want to talk to solve?
None of those things will be solved today.
I gotta leave in 20 minutes.
No, we should make one.
I had no I had no idea the two of you know each other. Do you
I know everybody.
No, you didn't know me until we had the couple.
I knew Mark.
You knew Savi?
Yeah.
Galileo.
Because we interacted with
Yeah, I know quite well.
yeah,
No, no, yeah,
former,
we don't, we
student
figured it was
of mine,
Italian, so I don't know how, I don't know how
Peter
to
Calvin.
Oh, I had no idea you were Peter's friend.
He didn't talk much Welsh. I don't blame him.
But he doesn't travel at all, as you all know.
Why
Oh!
he's nice. He's a
No, he's still at JPL.
Oh, he's at JPL? Okay,
No,
okay.
he never quit science, but he doesn't travel because he is into this
Yeah.
the Earth
Exactly.
and not much
Yeah.
carbon of
Yeah.
footprint and etc., which I think is not very good for his children as they don't get to know their grandparents. And I love the environment, and I actually understood science
Yeah.
because of for a couple of years, a
Yeah.
long, long time ago. But I put family first, and then I want to save the environment. But he published a book actually. You should find his books. It's about living with the smallest carbon footprint. I have no idea what's the title, but search and you will find.
Yeah, I'll find it, yeah.
It's like you have not been really in touch
No, I haven't been
with
in
him.
years. The last time I saw him was
He's
Caltech in 2000.
Oh, when he was still, when he was still there at the Ligo postdoc, I know. And then he moved over to GPL and he's doing climate science modeling, obviously.
The merger rate.
Anyway, I want to continue the discussion.
Oh, yeah, I'll see you.
Yeah, but
We can cut Skype at some point.
Yes, okay, so that is,
I want to introduce you.
I see what you're saying.
Hi.
I appreciate it. Yeah, so if you had this idea that you should.
I mean, it is, no, but I think, I'm just saying that's proportionality. I'm agreeing with you that proportionality is the case as long as you're replenishing the binary.
So you're
And so I think
so
you are assuming
do this paper,
state
and
binary.
then you have a problem which is
In a gas screen nuclear
investigates
star
like
cluster.
the different
Right, like it's gonna settle into some equilibrium, and if it goes forever, then you'll.
Yeah, so just send me an email.
Right.
About
At
it.
least you have some constant binary fractions, so then that's totally a fair thing to safely quiescent nuclear star clusters.
I can't
The
generate.
Good impact.
I think you
Like
also have to
3,
be
so.
the case, that you're gonna replenish, keep forming new binaries.
So I think they're gonna wherever they catch.
Worse than that, in the sense, again, as Mordecai was sayaying, we form,
Whatever they catch.
in any simulations,
Right.
we form binaries very easily.
Before 12 hours.
Trivially.
Because the first one they found
Very
was
short
12 hours.
So,
Like, they were
I would in fact,
But that's also because the rotates that the
I,
maximum amount of time it takes before an instrument is facing Earth and even is behind the sun.
Right, oh yeah, because, I mean, that's the thing, in principle, right, like if you just naively write out what you could get based on like, some can get,
Anything.
that was my point, you can get stupid rate. And so it sort of argues for,
There were just like a couple things that.
there's actually, and there's sort of a like,
Okay, we'll send me an email.
internet.
Okay.
So
The-
in 2 weeks or something.
Yeah.
At
Whatever.
some point, the
There's
assumption
Right.
that
But you're here until when?
Until end of
time scale
tomorrow.
of the AGM breaks down because the
Alright.
quiescent period isn't long enough to replenish and relax the cluster. So then there's like a minimum, and it is around like a megayar, right? But basically, everything interesting in our simulations
Erre még nem jöttem rá, mert teljesen más
Not
dolgon
a lot happens, everything slows down because you run out of stuff. But so if things get shorter than 1 megayear, then all of a sudden having a shorter lifetime gets to the rate. So, right, you get a few mergers and then it stops because the gas goes away and everything is interacting.
What are the things that you have?
Dynamically within the cluster, right? So there's some minimum amount
pH
of
also.
lifetime. So it could be, I mean, Aaron said this, I think.
You have to fit them both, it's not so precise, but then in both.
Now, we're talking about a different dynamical situation. You can't use
And I'll
this
check
filter, so you have to
feedback,
consider it like a year.
Accretion is like
Zinc particles.
zinc particles.
Zinc can be zinc particles.
After this conversation.
I have some criterions with angular momentum.
But
so
then there is this
I
question
have a
of
point
like,
of
okay,
mass.
so just feedback.
And this is coming, the gas is coming here.
So that it
I
doesn't.
compute the,
I don't know.
and
We are sort of
Two ways.
assuming, I mean, I think there's
The
a
matter
little
is
bit
gone.
of like the
The matter is gone.
SMPH issue where,
That could be a change.
you know, in Galaxy, the dynamic
or you
friction
compute
gets
angular
so
momentum of
close,
the order,
and then you need
compare with
individual
the sector
hardening events to get you
angular momentum of the
And I
outer
think
region of
the gas hardening is going to get you down to a certain centimeter axis. It's not going to get you down to the gravitational waves just totally take over. But what we haven't adequately modeled is there are these tertiary
newly formed
neighbor sun. Okay.
So is it possible to, as a result
So,
of fragmentation or something?
Yeah, we were only having.
Yeah, no, I know what you mean. It's like, you do all this.
Okay, formation of the zinc in the fragmentation. Yeah, I think that I can never use that. I can never use it. Like, I always put my zinc particles in the beginning.
All the time.
My initial completion has zinc particles.
Well, the
But
second
I
one.
know that in the code, I think you can create new zinc particles. Like I have a star formation, for
You're actually
example, so I think that you can create
apply to us at some level.
stars, zinc. You have to make a change because in Galactic we have a type of particles. So you have 0 types, like 1, 2, 3, 4, and 5. And that allows you to separate the kind of particles that are used. So it's only the thing of take the particles that are start forming in your stars, change it to what are zinc particles. That you have that is a star forming zinc particles.
And also
difficult to
right? That the energy like
you would like to do that or
Yes, so I'm considering to
I'm not worried about this.
I posted yesterday. So
Energy higher velocity distribution of your star if that's from the start, of course, you know, it doesn't all immediately go in. So what happens in the interaction?
You will have region of the stars, and that starts to have nova.
You sort of like you thought about this background
is or something similar is
you know, because there is this unknown heating source, right? I don't know how much you know about Agm Disk theory.
As much as you.
Okay, so, well, basically, right, there's this issue that if you calculate, like if you just calculate the mission Curtis Agm Disk, then in the outer parts, it should be ternary unstable. But it's not. When you go out and see the disks, they're not collapsing. They're not all collapsing into star formation in 1,000 years, for sure. So why not? There must be a heating source that's supporting the disk, and nobody has identified that heating source, actually. Binaries, or even just the stars that are orbiting through it, every time you hit the disk, you're driving, you know, if you've got like a polar orbit or anything really fast, you're gonna drive a shot.
Yes.
And even, you know, that's the stellar mass black holes, it's the stars, it's everything.
Yes.
A lot of events there that just keep hitting the disk.
It's the same that they chose. It's nice.
I wonder if that, and there's going to be more of them in the outer parts of the disk, exactly where the support problem is.
And I think that they
Right, just the number of volume goes up, the number of stars goes up. Huh.
Yes, but they propose some accretion
That is something you, I mean, like, would you be interested in working on that? Okay.
but they don't show some snapshot.
Like,
Just show
like, in some state, not ready.
mass functions.
Well.
I think
I might have fewer now after the first version, although those are white papers.
So it's not the
All right, cool. Oh, okay, all right, so, yes, nice.
Something with wind or star winds.
Yeah, no, thank you for coming, and I'm sorry that I ended up missing because I was teaching, I ended up missing your
You were.
yeah. But I caught.
Okay.
All right,
Nice seeing
cool,
you.
good seeing you, I'll see you again, hopefully soon.
So in this case, yeah, they have this. And then put everything particles gives winds, stellar winds, so give mass and momentum to the environment. I don't know if they, I think that they don't explode like supernova, but. Oh. So you can have that. This paper is quadro. Yeah, a creation of stellar winds in galactic center. I don't know if that one or that one. One of the two. 366. 366. So the paper is, and you can talk with. Okay, super nice. Dense, no. And Sergey is in Surrey, it's in UK, but it's super nice. And I was talking with Jorge and Sergey, and they were interested. They want to mold some of synergies with fragmentation, do some more work on that, so we can talk with them maybe. Yeah, they have this troubles. If you want to do this, you can tell Benz, or I can do it. I can write to Jorge. You give me your email and say if you want to do something similar, like put in contact with him, and then he has the code. Maybe he can send you the code. Yeah. Yeah. I guess Jorge will not have to change it. So if you want it, you can tell them, or I can write I think the only difference thing here is that they don't have stellar radiation, but supernova field, but that's at the end you have to think if you're in the PGB, what is your role at that time, because supernova explosions of stars that have formed in the disk will take something like 1 mega year. So you have to think how much you want to evolve the system. If you want to evolve it more than 1 mega year, then you need explosion of supernova. Or you're taking like already formed stars that they have already, well, you have to choose something. Or you can include explosions, right? That's not. No, it's not so difficult yet. Because if you already have the same particles, and you're putting in these simulations, Jorge is putting new gas into the medium, putting new, more thermal energy, so it's very easy to implement. If you model the explosion of supernovas as thermal explosions, not like a kinetic.
Also, if I want to integrate
then you can do it. Yeah, you can do it. If you have already, if you want to include kinetic energy sister, I think because you can do it in two ways. You can put new particles, of the gas particles, or you can give momentum to the gas particles that are close to the spin particles. And like you have, then the thing that's more difficult is to evolve the spin particles and be like this is a parallel code. You have to be aware in each spin particle which gas particles are around you. And that's the toughest, the most difficult thing. But if you already have that, if you have the particles that are close to your spin particle, then you can give it whatever you want, like more mass, more momentum, more energy, more temperature.
Yeah, and I'm just gonna plug this bad boy in.
You have from like a put it in the code.
You can airplane if you have a...
I am not.
Yeah, it can be.
I'm plugging it in.
Okay, all right.
Yeah, after a lot of.
You want a snack, yeah?
Writing and finding back.
Yeah, fair enough. Yeah. I don't want the last speaker.
If you already begin with this code, with Jorge, that.
I'll get you.
Then something above this code is not difficult. In any case, this is Galactic 2.
Yeah, so you want to plug something.
That is super similar.
Yeah.
Just let me do it my way.
Yes, Galactic 2. And you said you 3, but it's super similar. There are small changes, but maybe for this problem it will not matter too much.
So basically there is
Spin particles with wings. Each star has a wing. So it's fragmented.
If I could,
Each part of
like, share.
with a you use a criterion,
Spare.
density maybe, something like that, or the convergence of the slabs. And then if the heap of density increases, we form a star at critical matter, and also deliver to the medium wings. Maybe the two.
Cool. Got a choice.
Oh, I need to reload. We'll be good at this. Definitely. I guess we can sort of.
No, it's a region.
Some wish.
So it's the central region is accreting the winds from the stars.
Yeah, I would certainly invite you to attack them.
Yes, Sagittarius stars is accreting the winds.
Yes. Yeah.
The winds from the stars are generating an accretion around the central.
Absolutely. That's how it
This
got
is
from.
from
So Vlad, basically Vlad was supposed to, these guys were, and
from a star.
that's all it was, got started 6 years ago.
They have a star.
Yeah.
6 years.
Yeah.
Right. Yeah. Well, hold on.
I'm saying I'll be there.
Ah, fantastic, yes. Yeah, definitely
Yeah.
meet up then.
The answer is a relatively short amount of time.
He ordered me some ethers, so
Yeah.
that's theoretically a thing. So you guys know.
Yeah.
I don't know what's gonna happen, but things
I
are
don't
gonna
know.
happen.
Yeah.
Awesome.
Oh, I dragged it with me every day. Go in my bag and get my in the front zippy pouch is air.
In any case, I have the recipes for star formation for supernova.
The black case.
If you need it, I can.
Oh.
My recipe for star formation is for larger scales. So I don't know if it will be.
This is like,
You can use the same for a smaller scale because at the end you will form each star that you will form will be a single star.
Who the hell is
When I use this code, I use it for parsec scales. So much more larger scales.
Yeah.
Yeah.
Form one star particle in my case is a collection of
But it's just got that vibe.
1,000 stars, so it's different.
We can't patent the enthusiasm.
But in this case, it's large scale. That's I think.
They're working on.
Yeah, no, it is.
Yeah, absolutely. Yeah, that was on our radar.
Is that LIGO?
Okay.
LIGO is.
I promise
I'll make it painless. Hi, Fabio.
But now I'm like, yes, you are going to tell us more about AGN than we learned in the last 50 years from AGN. Like, you are averaging over all of the local AGN in the.
Oh, it's okay.
You are telling us like, holy shit. Like, you're easy in the field. You're like just.
No, nobody here.
I won't even tell you.
No, there's nobody here. Well, I'll just. Not you. If you want.
Okay, everybody, I think we're gonna get started. I promise I'll make this short and hopefully painless. And we're gonna, but I definitely, absolutely want to say thank you to the wonderful staff here. I have to say, like, let us thank them. Happily involved with organizing this and organizing other workshops, I can confidently say that workshops and things that get organized here, never smoother, never more wonderful. So grateful.
Thank you so much.
Yeah, really, yeah. Thank you very much.
That was my plan all along.
So, yes, in the acknowledgments to all your papers, please thank them. And thank Barry as well for leading the SOC, I think. Yep. And yes, but I am going to say a couple of other things. So this is just like my takeaways of what I think that I understand after this workshop, and I'm grateful to all the participants. Of course, many people have had to go early. So please shout if you think that I have missed something. So I broke it down just sort of by the various main sessions, and I think under the dynamics session, in terms of gas-free nuclear star clusters and trying to understand them, their rotation, modeling them with rotation is really important because that changes their dynamics. This is the inputs to anything that's going to happen with an active nucleus. Fabio, who actually just did have to leave, we had a little chat, and I think we actually now agree on the sort of relative rates that you can expect from gas-free nuclear star clusters and from AGN disks. Basically, the argument applies as long as you keep forming binaries at a pretty steady state, and he said that's good for nuclear star clusters, and that's certainly at least good it seems to be at least good for AGN disks. But that means that this is going to be our input distribution. And so that initial velocity distribution is going to tell us a lot of things about the AGN-driven rate. We need to worry about black holes with other things in binaries and what are the outcomes. And this I thought was a very interesting point, that we might be able to constrain what that velocity distribution is in our own galactic nucleus and what the history might be by looking at the CDs that are near Sagittarius star, because they are a very interesting, obvious binary probe. In terms of the gas disk, I think we need to know what the density is, we need to know what H over R is, and we need to know what the lifetime is. Well, so yeah, so and it would be really also good if we knew the temperature and the opacities. In situ star formation may or may not matter. It depends sort of on how much time you have to do star formation and to donate stellar mass black holes during a quiescent period versus an active period. But this is probably going to matter more in the outer disk than it is in the inner disk, just on a volume argument. So that, I think the outermost disk of the AGN is probably the most gnarly and difficult to treat. So outer disk could be very important and is incredibly challenging. Our models should be informed by observations, and in particular changing look or changing state quasars, whichever you'd like to call them, maybe a really interesting probe. They might be an unusual subclass, but they're not totally infrequent. And they may be telling us, they may have the capacity to tell us a lot more about the structure of AGN disks than other relatively normal AGN disks. And in particular, right, one thing that we would really like to know is, can we get migration traps in AGN disks even before you put anything into them. And what's really driving migration traps is d sigma dr, what is the mass density as a function of radius. And so if we could get a better observational handle on that, possibly from timescale variability arguments or from other channels, then that would be pretty useful. Yes.
Note that that relates back to the requirement for temperature and opacities, because that actually determines that.
Right, exactly, right. That's sort of, yes, right. That has to be why that is in there. But we might be able to measure, I don't know. Yeah, I don't know what's going to be easier to measure. It's going to be heinous.
Are we just skipping Mike's now? Can you all hear me? Yeah?
No one online.
Oh, yeah, there's, sorry.
Yeah. I mean, if there's no one online, I can just shout. That's fine.
Yeah, that's fine.
Okay, yeah.
Well, there's also the recording.
Oh,
We're recording.
Okay,
Pass it out.
All right, here.
Posterity needs to hear my every word.
I'm sorry. Why are you interrupting me?
Oh, no, it's just that. Just add, d sigma dr can tell you about additional sources of pressure in here. So magnetic fields may provide, if you wind up a whole bunch of magnetic fields, and that adds an additional source of pressure, then density, the temperature, and the opacities are not enough to give you the total pressure and the full sort of H over R. So it'll tell you also something. D sigma dr is also going to tell you something about the B field. Sorry.
Okay, cool. Once we add the stellar mass black holes, you'll notice actually as I go from here to here, like the print gets smaller because the list gets longer as I'm trying to fit it onto one slide. And so like the life gets more complicated. We do need to pay attention to the fact that AGN disks have parts and different regimes, right? The inner disk and the outer disk, which I just mentioned, is, but we may also have to think about how the dynamics of a nuclear star cluster be affected by some of the other parts, including is the corona even enough to mess with dynamics? Is the warm absorbers enough to mess with the dynamics in ways that matter? And again, the thing that I've said I think a few times at this point that keeps me up at night, is there a possibility that there are simply quiescent disks that are just big and massive and messing up dynamics, and we don't really have any, they're not actually accreting onto the black hole at the moment, supermassive black hole at the moment for whatever reason, and so they are dark. So let's hope that doesn't exist. We would like to look at our single objects around SMDH and try to understand what feedback is going to do to things like the migration torques. So I think this feedback has the capacity to impact the migration torques, and it has the capacity to impact the ability of the disk to accelerate binary formation. And so, you know, among the sort of near-term questions, I don't know if we can firmly answer them, but hopefully we can make a little more progress in this direction, as I know people are already, you know, moving that way. But let me encourage. It might be worthwhile to look at a binary and a shearing box with a realistic H over R for an embedded binary in an AGN disk, because most of what's driving the hardening there is the local gas. And so we don't necessarily need to simulate everything, but to the extent that differential rotation may impact it, we can maybe get away with this and answer some questions, at least coarsely. And indeed, is that going to drive eccentricity? Is there going to be some limit, or is it where it's going to get damped? Is the gas necessarily going to cause hardening? Could it cause softening, right? If we have the right kind of feedback in the wrong way, that could be the case, and then this channel is DOA.
And all that with feedback, obviously.
Right, so feedback is, you know, we can do this if all we have to care about is gravity, right, at some level, but it's the not only gravity that makes life measurable. And also enjoyable. You see, not just gravity. Electromagnetic interactions. Okay. I think so far also we've largely ignored the fact that there are other objects that are going to be in here, not just stellar mass black holes, and that is something that we ought to start paying attention to. And I'm saying this for myself. And in particular, right, there's definitely concerns about three-body interactions and whether they might be necessary. So far, we've done silly things here because we don't have detailed simulations of what happens. as the semi-major axis shrinks, and we've just said, okay, let's just assume gas hardening works all the way down until the gravitational waves take over, and that's almost certainly not true. Which is why I said my plot earlier about the timescales, I took things extremely literally. I did literally the simplest, I'm not even going to call it algebra, I'm going to call it like arithmetic. I literally did arithmetic and said, let's just be dumb and see what happens, like what's the worst case scenario. So, but we can sort of get a little smarter there, that would be good. Grind down into the disk. So again, there's lots of objects where we've been largely dealing with circular coplanar things. Some people have gotten very excited and fancy with eccentricities, which is great. We should start to pay attention to that. And I think we started to treat drag, but we haven't started to think about what, there's migration torques, there are vertical migration torques that are going to matter, and those are difficult to treat. And I will just note that they might dominate. Okay, the list gets longer and smaller. So we have observables. So the good news is we've got lots of observables. So I did of course miss this morning. I apologize, I was teaching. But very many people filled me in, so if I missed something, please tell me. But there's a lot of discussion of AGN variability. Do we know what waveband, what the duration of variability is? What is the time scale of, or duty cycle? Actually, I think I meant to say cadence there. So like what's the duration and time scale of the event, and then what is the appropriate cadence for observing it? And this is obviously an important thing to consider with LSST coming up, and they haven't settled on their cadences yet, right? So there's still an opportunity for community input if we think that we need something substantively different for some good reason, at least some fraction of the time, we should tell them because they might do it. I think things that are important for observable capabilities that are not going to come for free, right, that are not already approved and planned and budgeted and hardware is being cut as we speak. I think that, ultraviolet and X-ray are important wave bands, and we do have E Rosita coming up, which is good. We have Athena, which is great, but there's not a lot between E Rosita and Athena. Chandra is not going to last forever. This ultraviolet is probably even in worse shape. Swift is not going to last forever. Hubble is not going to last forever. And then we have nothing. And we can't see that from underneath the atmosphere. So unlike other wavebands. Well, we can't see X-ray underneath the atmosphere either, but we have plans for that. Polarization, so that just came up in the last session, which I thought was really interesting and is probably worth thinking a little bit more about because the inclination angle enables us potentially to shrink the LIGO error box in terms of volume. So just to reiterate, and I can see she's like smiling and nodding, okay? If you can, there is a degeneracy between the measurement of the inclination angle of a gravitational wave source and its distance. So if you did not know that, right, remember that. If you can constrain the inclination angle, then you can shrink the distance error box. So, or if you could, on the other side, if you could magically figure out which galaxy it is, and then you know the distance, then you can constrain the inclination angle. Yeah, so polarization might be one way to do this. For the waveforms, obviously people have talked a lot about eccentricity. That's very observable, although it's probably, in a lot of cases, it's gone by the time you get to the LIGO waveband. But if it's not, that's great. There are potentially extra accelerations. Again, they're probably mostly gone by the time you get to the LIGO band, but if they're not, gas drag, obviously extra accelerations. So the smoking guns that I think I heard, that I think that everybody agrees with, I think, is if you see a source, if you got enough cycles on a stellar mass black hole source and it was orbiting around an SMBH, then we would just see the Doppler shift of that, and that's, right, that's great. The Kozai leadoff oscillations, but it's not clear how these would be impacted by the presence of gas. So these predictions might have to be refined a little bit, but these are certainly, these are certainly promising. We heard from Andrea, phase shift, which will definitely be measurable by LISA, although not by LIGO. LIGO to LISA band.
Just to be clear, the Doppler shift is also a LISA measurement, right? Or did I miss that?
Most likely, I think, well, so it depends on, basically, right, the Doppler shift depends on how long you can get it in band for.
Yeah.
So if you've got a really massive thing that happens to be merging pretty close by, and it's after the upgrades so that the sensitivity is higher and the signal to noise is bigger, then if you get enough cycles to complete enough of an orbit, right, and how far out is the orbit?
Yeah.
Right.
Okay.
So it's just that's what's constraining it. How long do you see the signal for, and how long does the orbit take? So if the orbit around the SMBH is sufficiently short, then it requires getting pretty lucky to see the LIGO, but it's not maybe totally beyond the realm of plausible. Yes. Oh, Carl, did you have a?
No, not really. I mean, if you put it in these resonance traps, right, that's a 500-day orbit.
That's hard.
Yeah. So unless you can get it, and even then, the redshift, I mean, the Doppler shift will look essentially similar to the redshift, right? Because then even if I can instantaneously measure it, I'm getting a Z of 0.04 or 0.05. So.
But it's time dependent.
Yeah, if it changes. Yeah, but that's my point. You can instantaneously measure it for LIGO, but you really need to cover a significant fraction of the outer orbit for the change to be observable. Like even if you have a several hour waveform, I can't imagine that's still only covering 1/1000th of the orbit.
Yeah.
It's systematic for the dub.
Days?
Say what?
You're gonna pass around the mic.
Oh, sure.
Sorry.
So the most optimistic case is if you have an eccentric orbit, which is in the band for longer, and if the masses are smaller. So suppose you have a very eccentric neutron star binary, which could be in the LIGO band for several hours.
Oh, okay.
But still, you need.
Long? Really?
If it's eccentric, yes.
Yeah.
Yeah.
Neutron stars, a normal neutron star can be up to 30 minutes. It doesn't take that long to get the functioning on.
Yes.
It can be many days.
It can become many days in the band. The question is if the signal to noise is high enough.
Yes, I know.
But you have to have it close to the supermassive black hole to.
Yeah, and also it's harder to form gravitational wave captures with neutron stars just because their capture radius is so damn tiny.
Yeah. Dan.
Oh, yeah, I don't think I have much more to say except for at the inner migration trap you have a 3 hour orbit, right? So can you get a significant fraction of that?
That would be nice.
Yeah.
Oh, and Z is like 0.4 then.
Yeah.
Yeah, that'd be
Right.
very nice.
Yeah.
So maybe, but probably LISA. So phase shift measurable by LISA, but probably not by LIGO. In an individual source, it's being gas driven. Although this does depend, well, it's not gonna be measured by LIGO anyway. LIGO to LISA band timing, and then the possibility of a high mass ratio merger, and then I added the caveat of messed up spin, right? Because in the case of the nuclear star cluster, we have very firm prediction for what the spins will be. In the case of the Agm disk, it could be something else. And so if you see something that you might otherwise want to attribute to a nuclear star cluster, but the spins don't match, then I think that is not an unreasonable thing to expect to see in an Agm disk. So then, or you just forget about all of that and just wait until we get 1,000 events per year and use that to figure out everything else in the previous 4 slides.
The observers do the work.
So basically, assuming that the gas disks glow, and we can figure out from that what the contribution is, what fraction of the contribution can be associated with Agm disks, then we don't have to predict the eccentricity, spin, redshift, and mass ratio distributions. We'll just ask you guys for them, and then you'll tell us, right? And then we can tell you from that what the AGM disks must look like in order to produce those things. So
solved.
You just have an inverse problems.
Yeah,
right.
exactly. Yeah.
And having said all of that, of course, I will also add that there are an inordinately larger number of data points and an inordinately higher resolution information about protoplanetary disks than there are about AGN disks. And I will share with you one piece of data from a messenger that we will almost certainly never get from an AGN disk. So this is a carbonaceous chondrite. If anybody wants to, this is my meteorite from my meteorite collection, because I am that crazy. And yet the protoplanetary disk people are still arguing over what the right models are and how to deal with it.
Idea how,
right.
How to do this.
No. We have ideas. It's just that we have evidence and we have ideas, and they're not sufficiently constraining.
So maybe feedback from Ligo can help us.
No, but I think
put that in your next proposal.
So here is the contrast, right?
Yeah.
That's the one thing that we don't know.
Right.
Yes. Well, the matrix too.
The matrix. Exactly.
And since this is the actual fossil,
yeah, we don't know the bubbles, we don't know the matrix.
We don't really know anything.
These are things that
yeah.
we can touch.
Yeah. So having said all of that, so I put my super optimist hat on, saying, look, Ligo will answer all these questions for us and tell us everything about AGM disks that we ever wanted to know, except in the protoplanetary case, by analogy, even with almost infinite amounts of information by comparison to what we will have, they still don't know what's going on entirely. So all the theorists will have work for many, many years. Yay! Yay! So yeah, so I think that was all I wanted to say. Is there anything important that I missed? Thank you, everyone. This was wonderful. We really appreciate you coming.
Thank